Welcome back to Victorian Physics. Today, we're going to go over Coulomb's law. Now, this law is an equation that demonstrates how electrical force is created. And in terms of electrons, it's going to be your best friend. So, how the equation goes is that F, which represents force, is equal to Q1, or charge 1, times Q2, or charge 2, divided by r squared. R represents distance. And you're going to want to take that and multiply it by K, a number we call the Coulomb's constant. The Coulomb's constant is actually a lot more complicated, has lots of decimals and stuff, but you can round it up to 9 times 10 to the 9th power. We're going to go over that number a bit later, but for now you can just use that number. And there, you got Coulomb's law. Now, when it comes to electrical force acts differently depending on the types of charges in the system. If both charges are positive or both are negative, then they'll repel. But if one's positive and the other's negative, then they'll attract. Typically, Coulomb's force is about taking the magnitude of the force, so you'd take the absolute value of both charges. But if you need help remembering whether or not the force is repelling or attracting, then you can use the rules of multiplying positive and negative numbers. Then you can just keep the negative signs when the charge is negative and see, oh, is it positive? That means the two are repelling. Oh, is it negative? I guess they're attracting. But make sure to remember that Coulomb's law solves for the force magnitude. So don't write on your test that negative force is attractive. That's not a thing. This is just to help you guys if you have a hard time remembering positives and negatives, which is important because, oh my god, the negatives in physics get tricky. Don't worry, we're not there yet. To better understand how this law works, it'll help to look at how it was formulated in the first place. So let's start by taking a look at Charles Augustin de Coulomb, the man who the law was named after. And before you ask, yes, most, if not all laws, are named after famous scientists. Charles Augustin de Coulomb was born in 1736 in Angoulême, France. He later moved to Paris to study mathematics at the Collège des Quatre Nations, and then enrolled into military school, specifically in Mezieres, in 1759. He graduated 2 years later and then went to work in the West Indies as an engineer. He worked there for 9 years, but had to come home after experiencing some health problems. Ah, what a wonderful thing to be home after all these years. I'm so glad to have come home. Now I can live the rest of my days in peace. On second thought, maybe I should have stayed overseas. Fortunately, he wasn't killed by the carnage that was the French Revolution and managed to make some discoveries after returning home. One of those famous discoveries, Coulomb's law, first came from Thales' discovery in 600 BC, which found that when fur was rubbed against amber, that amber would attract other materials, like feathers. Over time, other philosophers and scientists would recreate similar circumstances and even create repulsive forces between different objects. People started seeing patterns between these interactions. However, there was usually some confusion between electric force interactions and magnetic force interactions. Thankfully, William Gilbert, an English physician, conducted experiments such as his famous lodestone experiment to study these forces and was able to differentiate them. He published these findings in his text De Magnete, where he first referred to electric force as electrum, referring to the Greek word for amber, electron, the object where this effect was first observed. Later on down the line, this word would turn into the terms electricity and electron. Gilbert's discovery sparked an interest in electric force from lots of physicists, and one question they all wanted to answer was, how do we measure this force's magnitude? One guy, John Robinson, began to experiment with electric force, and found that the force would change whenever the reciprocal of the distance squared was changed. Joseph Priestley, another physicist, also found this pattern and even wrote about the idea. Eventually, Coulomb started reading Priestley's work and gained an interest, deciding to run his own experiments as a result. He first set up a needle on a torsion spring and put a pith ball with a charge on its tip. He then used another ball with the same charge and held it near the needle, seeing how it moved away. He found out the repulsive electric force between the two balls was inversely proportional to the balls' distance squared, as predicted. This experiment worked perfectly, except for one little thing. While this worked for balls with the same charge, when opposite charges were used, needless to say, it was back to the drawing board. To fix this, Coulomb created a new experiment with a suspended needle that had a charged plate on its tip, and used a hollow metallic sphere with a 6-inch radius to get the opposite charge. The sphere was used as a giant point charge and was held at different distances from the needle's plate. He would then give the needle a gentle push to give it some velocity, and then measure the period of oscillations, or time it took for the plate to swing from side to side at different distances from the sphere. Although the velocity of the plate wanted to move in a circle around the needle it was attached to, based on centripetal acceleration, it kept experiencing a force that pulled it towards the sphere. Every time the plate started moving away, the velocity would decrease until it started moving back. By calculating the time it took for the plate to swing back and forth, Coulomb was able to calculate the force and found that, like repulsive electric forces, attractive electric forces are also inversely related to distance. Coulomb published his findings and ended up getting credited for this theory. Eventually, these numbers were put into an equation. F is equal to the charges of both objects, since electric force is generated by charge, times K, Coulomb's constant, divided by R squared. Now, about K. Coulomb's constant is equal to the value of 1 over 4 pi absolute naught. Absolute naught's another constant, by the way, but it's typically recommended by the CODATA organization to use the value of 8.987551792 times 10 to the 9th power as K. Wow, that was a mouthful. Sometimes physicists need to be very precise about their measurements, but if that's not important to you, like say you're taking a test and your teacher doesn't want to read out all those decimals, then you could just round it up to an easier number, like 9 times 10 to the 9th or 8.99 times 10 to the 9th. Okay, so now comes the big question. Why was any of this important? Well, look around. Everything we use nowadays is powered by electricity, which is caused by electric force. By using this law, researchers and engineers were able to harness the power of electricity and incorporate it into our everyday lives. Telephone calls, medical equipment, even something as simple as a flashlight. All of that comes from electricity. Also, despite being different from magnetic forces, Coulomb's law helped other physicists like Simon Denis Poisson create more calculations for magnetism and expand their knowledge of that field. This law also provides the basis of lots of fundamental chemistry concepts. For example, the periodic table which was developed by Dmitri Mendeleev has trends that are explained by Coulomb's law. Like, did you know that the atomic radii of elements gets bigger as you go to the bottom left corner of the table? This is because as you go down each row, an extra shell of electrons is added, making the distance bigger. But as you go to the right, the amount of electrons on the outer shell increases, making the charge bigger. I'm not going to go too into depth right now, but I really recommend looking into it. I actually might end up doing a video on it in the future. Chemistry might be a different subject, but it overlaps with physics a lot. Wait, what was I talking about? Oh yeah! So basically, Coulomb's law served as the foundation for the scientific principles that expanded our knowledge on electricity, magnetism, and chemistry, to the point where now we have all this incredible technology. Without this law, society would be completely different from what it is today. Thank you all for watching. I hope you enjoyed that. Sorry for not posting 2 weeks ago. I had to go on a break for school reasons. Please let me know what you thought of my video and what you'd like to see in the comments below. And don't forget to like, subscribe, and I'll see you all in 2 weeks. Bye!